Okay, there are two types of resonant circuit: series resonant circuit and parallel resonant circuit. Okay, so what we'll be discussing here? So we'll be discussing about the definition of resonance. What is resonance? Okay, what is resonant frequency and what is bandwidth and what is the quality factor? What is the quality factor at resonance? Okay, we will be having some derivations part. It is part of your syllabus, and I'll not be deriving such equations. It is left to you, and it may be asked in the assessment. Okay, so some derivations I will skip here, but it will be there in the syllabus, and it is part of the assessment process. Yeah. So, what is resonance? So, what do you mean by resonance? So, it is a phenomenon. It is a phenomenon which occurs. Phenomena which occurs in a AC circuit. Resonance is a phenomenon which occurs in all kinds of AC circuits containing the passive elements R, L, and C. So when elements are connected in series, it becomes a series resonance. When elements are connected in parallel, it becomes parallel resonance or anti-resonance. Anti-resonance. Okay. So it is a condition. It's a condition which the reactances gets cancelled. The reactances gets cancelled. That means so there are two kinds of reactances. Reactance is denoted by X. So reactance due to the inductance is XL, and reactance due to the capacitance is XC. Okay. The inverse of reactance is susceptance. This is inductive susceptance, and this is capacitive susceptance. This in the circuit, when XL becomes equal to XC or BL becomes equal to BC, there we can say that resonance has occurred. It means the power factor of the circuit becomes unity. The power factor becomes unity. That means power factor, that is cos phi, becomes equal to what? 1. And the circuit behaves purely as a resistive circuit. This phenomenon, wherein which the power factor is unity and circuit is purely resistive. A circuit is purely resistive, then you can call that as resistive resonance. Okay, so it's a very important phenomenon, basically in the field of communications. In the field of communication, so where in which you will have to select some frequency. That means you will have to select the desired frequency transmitted by the station. For example, in your FM, there is frequency modulation devices. So you tend to select a certain frequency. For example, 100.6 megahertz or 97.3 megahertz, like this. You tend to select these frequencies. How do you select this frequency? You resonate. You resonate your receiver with the transmitter. Selection of desired frequencies. Okay. So the receiver rejects all other unwanted frequencies except this selected frequencies. So this is nothing but the phenomenon or principle of resonance. Okay. So here we study two things here. That is Q factor. Q factor is nothing but quality factor. It is nothing but a ratio of maximum energy stored, maximum energy stored per cycle to energy dissipated, energy dissipated per cycle. So energy store, the storage of energy happens in uh, two parameters or two passive elements. So what happens here? The energy storage happens in inductor in terms of magnetic field and in terms of electrostatic field in capacitors. And energy dissipation occurs in all the resistive circuits. So you will have to find out what is the maximum energy stored per cycle in a given circuit. And also you will have to find the energy dissipated per cycle in the same circuit. If you take the ratio, then it is nothing but the quality factor. Okay, so it is nothing but the efficiency of the circuit elements to store the energy, and quality of the circuit elements will be notified by using this factor. So it might be of an inductive circuit, it might be a passive circuit. If it happens to be an inductive circuit, so the energy stored. So what happens here? You can write the equation like this. So when the circuit is inductive in nature like this, that is R and L, the energy storing, that is energy stored and energy dissipation, you can write like this. So what happens here? It is nothing but half Li square is energy storing, energy stored, and I squared R. I squared R is your power dissipation. Okay, that is nothing but I squared R. Okay, so what is that you have to take down here? Okay, this is what expression for energy storage, and this is expression for energy dissipation. So take the ratio and multiply with a period, that is 2 pi. You will get quality factor as omega L by R, where omega is nothing but 2 pi f. Omega is what? 2 pi f. Okay. So this is the quality factor for the inductive circuit. Okay. For example, if you want to do the analysis in a capacitive circuit, so it's nothing but half CV square, and energy dissipation remains same, it's half CV square. Okay. Similarly, if you take the ratio of those things, so you will be getting Q as 1 by omega RC, where again omega is what? 2 pi f. So the derivation I'm just leaving it to you. The ratio remains the same. So it is nothing but energy stored to energy dissipated. Okay, per cycle. Nothing but what? Per cycle. One cycle is how do you denote one cycle in an AC concept? So this is one cycle of the wave. This is 0 to 2 pi. Okay, this is how you denote one cycle. So what is the energy stored here in one cycle, and what is the energy dissipated in one cycle? So you take the ratio there, then you will get the quality factor. Okay, so what is the frequency? Frequency is what 1 by T. F is what 1 by T here. So this is how you can denote this quality factor. Okay, so frequency of cycle. Yes. Next is a very important thing. Without this knowledge of quality factor, you will not be understanding the phenomena of resonance. Okay. So when does the series resonance occurs and when does the parallel resonance occurs? There is a next question. Okay. So series resonance occurs when elements. This is for series resonance R, L, and C here, and it is connected in across voltage source V, and current is flowing I here, R, L, and C here. So what is the total impedance here? The total impedance is R plus J times into XL minus XC. Why this J? J because it's an operator. J is 1 angle 90. The voltage across the inductor leads the current by 90 degree, and the voltage across the capacitor lags the current by 90 degree. Lagging is positive and leading is positive and lagging is negative. You can consider respect to the voltage as a reference phasor. Okay, so this is what I meant to say. Z is equal to what? R plus J into XL minus XC is R plus J times into XL. We already know that is nothing but omega into L minus 1 by omega C. So this is what the expression for the impedance. So as I said, when does the resonance occurs? The resonance occurs when the reactance part is 0, that is the reactive part is 0. That means omega L minus 1 by omega C is equal to 1, 0. So at resonance, omega is denoted as naught, omega naught here. So omega naught L into L is equal to 1 by omega naught into C. So omega naught square is equal to 1 by LC. So omega naught is equal to 1 by root LC. So it is 2 pi F naught is equal to 1 by root LC. Therefore, F naught is equal to 1 by 2 pi root LC. This is the frequency at which the capacitance, inductive capacitance becomes, capacitive reactance becomes equal to inductive reactance. So this is where the power factor of the circuit becomes unity. This is where the circuit behaves purely as an resistive circuit. So this is the frequency. Okay. So at resonance, the inductive reactance is equal to what the capacitive reactance. This is what you have to understand. Okay. Yes. So next concept here, you need to remember this. F naught is equal to 1 by 2 pi root L C is the series resonant frequency. Okay. So next concept is how the frequency, the phasor diagrams with respect to the voltage. Okay. And the currents you can note down. So phasor diagrams. So if you take I as a reference phasor, so the voltage here across the inductor will be at an angle 90 degree. That means voltage leads the current by an angle 90 degree. So this is the current will be in phase with the voltage across a resistance, and the voltage across the capacitance lags the current by 90 degree. So this is VL, this is VC, and this is VR. Okay. So for an inductive circuit, for a capacitive circuit, and for an resistive circuit, so what would happen? So the three different frequencies you can say here, the voltages developed across R and then C and F is less than F naught. So frequency, for frequencies F is less than F naught. So F is less than F naught means what? XL is less than XC. That means voltage across inductor is less than voltage across the capacitor. Okay, so this is the first thing. So where, so you will get like this. So it is the resultant phasor like this, and this is VC minus VL. That means here the XC is greater than XL. The circuit is capacitive circuit. The circuit is what? Capacitive circuit. Okay. So you can also write the things for an inductive circuit like this. Similarly, you can write for an inductive circuit. So right now, so write the current phasor as it is, and this is VL and this is VC. So F is greater than F naught in this case. So obviously omega into L is greater than omega C. That means your XL is greater than XC. That means your VL is greater than VC. Therefore, you will get VL minus VC as a resultant here, and this is what VR. So you will get a resultant phasor like this V. Okay, this is nothing but a purely inductive circuit in nature. So, okay, similarly, you can also write when XL is equal to XC. So this is VL as it is, and VC as it is, and this is I as it is, and here VR as it is. So here F is equal to F naught. So omega L is equal to omega C. XL is equal to XC, VL is equal to what we see. Therefore, you will get VR in line with the resultant phasor will be in phase with the voltage and the current. So in this case, the circuit is purely a resistive circuit. So this is how the different circuits behave under different frequencies with respect to the resonant frequency. Next, you can also comment upon the reactance curves. Now, is it okay? Hello? Am I audible?
Yes, sir. It's okay, sir.
Yeah. Reactance curves, we can write. So, XL, I said XL is equal to what? Omega L. XL is equal to what? Omega L. So that is nothing but 2 pi FL. So if I go on increasing the frequency, so what happens to this XL? So what happens to this XL? So when I increase the frequency, the XL also, this is X, sorry, it is X here. So the X also tends to increase in a straight line like this. So this happens to be what? XL. Okay. So this is with respect to what the inductive reactance curve, and this you can repeat it for the capacitive reactance also. So try to write the curve for capacitive reactance. XC is equal to what? 1 by 2 pi FC. As you tend to increase the frequency, so what would happen? The XC would decrease. The XC would decrease. So as a result, the curve would come here like this. This is plus X and this is minus X. So you will get XC as like this, 1 by omega C. Okay. So this is how you can write the reactance curve based on the variation of frequency. Okay. So the point on the frequency axis when total reactance crosses the frequency curve, frequency axis indicates the condition of the resonance. Okay. Yes. So what happens to the current then? So we discussed about the voltages, we discussed about the impedance, the reactances now. So what happens to the current here? So let me write down as R is equal to what? Z is equal to R plus J into XL minus XC. So magnitude of Z is equal to what? Square root of R square plus XL minus XC whole square. So the magnitude of Z will be equal to what? R at resonance, because at resonance XL becomes equal to what? XC. That means the impedance of the circuit is purely resistive in nature. Okay, so at resonance the Z will be equal to R, as the reactances becomes equal to what? Uh, becomes equal. So therefore, the impedance was higher at all of the frequencies at resonance. The impedance becomes equal to what? R. So the impedance will be minimum. The impedance will be minimum and will be equal to what? R. So this is how you can write like this. This is F and this is Z. Initially, the Z will be like this. As the frequency increases, the Z impedance decreases and then increases. At some point, at this point, the F naught. F naught is the resonant frequency. At this frequency, the Z is equal to what? R. It is the minimum value of the impedance which will be seen at the resonant frequency. Okay. Now what happens to the current? So you can also write when the impedance is decreasing. Okay, the impedance is here decreasing. So what should happen to the current? So when impedance decreases, the current should increase. Okay, like this. So this is what I naught, and this is F naught, the frequency, again F naught, the frequency, and this is Z is equal to R, and this is nothing but I naught. At resonance, the current will be maximum. The current will be maximum, and that I value is what I naught is equal to what? V by Z. Okay, or is nothing but V by Z naught, or nothing but V by R. Okay, so this is how you can study the analyze the current, the impedance, the reactances in case of a series resonance phenomenon. Okay, so when you have written impedance, you can also write the admittance part like this. So for example, if the impedance is decreasing, so obviously the admittance should increase. Okay, this is what the Z, this is what the Y, this is F, this is F, and this is the current. Also you can write like this, and this is at all F naught. This is what I here. Okay, this is how you can write with respect to the Z, Y, and I. Okay, so what happens to the phase angle then? The phase angle is nothing but the angle between the voltage and the current. The phase angle is nothing but what? The voltage and the current. So that will be crossing. That will be crossing the frequency at some point of time. Okay. So what you can analyze, at this point and this point, the Z will be what? Capacitive here, and here it will be what? Inductive here. Capacitive in nature and inductive in nature. Okay, so this is what uh, the different behaviors of elements in case of a series resonant circuit. Okay, so now you have to derive an expression for the quality factor in case of a series resonant circuit. As I said, so quality factor is nothing but omega naught L by R for an inductive circuit on omega naught RC for a capacitive circuit. So quality factor for series resonant circuit you can write like this. So Q naught, if you just simplify it, so omega naught L by R. If you simplify it further, so we'll get 1 by R in the square root of L by C, because omega naught is what? 1 by 2 pi root LC, sorry, 1 by root LC. 1 by root LC, you just substitute here in this part and you will get this one. Okay, So this is how you can derive an expression for quality factor of a series resonant circuit. And next, we can derive an expression for the voltages. That is current we have already derived. That is V by Z. That is nothing but V by R. We can write it for VL. VL is what the current, the voltage across the inductor at resonance. So it is I naught into JXL. I naught into JXL. So, and VC is equal to what? I naught into minus JXC. So this is how you can do it. Okay. So also, if you want to simplify further, so this gets simplified as Q naught into V angle 90 degree, and this is plus Q naught into V minus 90 degrees. If you want to simplify it further. So this is voltage across the capacitor at resonance, current through the circuit at resonance, voltage across the inductor at resonance. Okay. So, and now you can discuss about few concepts here, that is bandwidth. Okay. Bandwidth and selectivity and half power frequencies. Half power frequencies related to series resonance. So what do you mean by bandwidth? So bandwidth is nothing but band of frequency over which the power in the circuit is half of its maximum value. But power in the circuit is half of its maximum value. So this is what we meant to say. So this is frequency and this is current. And if I write like this, the current at the maximum value, the power would bandwidth, if you want to define bandwidth, it has to be defined with respect to what? The power. Power in the circuit is half of its maximum value. So at this point, the power will be half. Okay, so this is F1 and this is F2 and this is F0. Okay, at this point, so the current will be is I naught by root 2. So why I naught by root 2? I'll explain here. Because the equation for power P naught is equal to what? P max, that is equal to what? I naught square into R. Okay, so P dash is equal to what? P naught by 2, that is nothing but I naught square R by 2, that is nothing but I naught by root 2 square into R. Okay, so at this point of time the current is what? I naught by root 2 at half power frequencies. So at this point, and at this point, the power is half. As a result, the current is I naught by root 2. So the frequency at which the power is half is nothing but F1 and F2. That is called half power frequency. And this is lower half power frequency, and this is upper half power frequency. Okay, so you can now define the bandwidth. Bandwidth is what? F2 minus F1. So it is the difference between the frequencies where the power is half. Okay, upper half power frequency and lower half power frequency. And this frequency is also called as 3 dB frequency because the power at this frequency is 3 dB less than that of the resonance, Okay, so there is one derivation with respect to the F f naught in terms of square root of f1 and f2. This is the derivation part. Resonant frequency in terms of half power frequency is very, very important. You can expect a derivation on this concept because there involves some mathematics. So I'll just leave it to you. It is very simple. You can refer it from any of the textbooks. So it can be derived by using the standard expression, that is I is equal to what, V by Z. So V by square root of R square plus XL minus XC whole square. And at half power, I is equal to what, I naught by root 2. So it's nothing but V by R. I naught is V by R at the resonance. Like this, you can simplify it, and then you will end up in getting the expression for F naught. I'll just leave it to you, the derivation part, and from that, if half power frequencies, we can define bandwidth. That is, we have already discussed, that is f2 minus f1. That in terms of this r by 2 pi l. Okay, this is and f1 is equal to f naught minus delta f, and f2 is equal to f naught plus delta f. So this is nothing but delta f, and this is also nothing but what, delta f. Okay, so we can derive one more terminology here, selectivity. Selectivity is nothing but ratio of resonant frequency by bandwidth, f naught by f2 minus f1. It is nothing but ability of the circuit to discriminate between desired frequencies and undesired frequencies. Ability of the circuit to discriminate the desired and undesired frequency. It is nothing but ratio of the resonant frequency to the bandwidth. Okay, so you can also write this selectivity in terms of the quality factor, that is q naught, that is f naught by bandwidth. So bandwidth is equal to f2 minus f1 by f naught by q naught. This is also possible. Okay, so you can say that the selectivity is directly proportional to what, the quality factor of the circuit. So what is expected in this concept from your side? So you should know what is resonance, what is series resonance, when does series resonance takes place, and what is that quality factor, how do you define quality factor for a series resonance circuit, and what is selectivity and what is bandwidth, the derivation of resonant frequency, derivation of half power frequencies, derivation of resonant frequency in terms of half power frequencies, and variation of inductances, that is inductive reactances with respect to the frequency, variation of voltages with respect to the frequency, variation of impedances with respect to the frequency, what happens to the current during resonance, what happens to the impedance during resonance. All these things you have to know as a concepts. Yeah. So based on these formulae, you can expect problem, very simple problem. Directly you will be given the data, you will have to substitute back on the required formula, and you can get the answers. Okay, so this is about the series resonant part. So I will not mix up the parallel resonance, the series resonance. So what we shall do, we shall solve some problem here, and then we can go for the parallel resonance. Okay, so take down the first problem. So the problem will be direct. Okay. So a series like this, a series resonant circuit has R is equal to 10, L is equal to 5 millihenry, C is equal to 20 microfarad. Find F naught, find quadrifactor, find I naught, and voltage is 100 volts. So everything, you have got the formula. F naught is equal to 1 by 2 pi root LC. Q is equal to 1 by R square root of L by C. And I naught is equal to V by R. Everything, you have got the formula, just simplify, you get the answers. Quickly do it. Yes, anybody solved? F naught is equal to?
So 503.29.
Yeah, correct. 503.29,
Q 1.58.
1.58, I
I not
naught,
10. 10.
10 amperes. That's all. So it is our 5 marks problems. Okay. So, so what I will do, I will just uh, stop at this point because I have a meeting now. I have to prepare for that meeting. So tomorrow we shall continue with series resonance and I'll start from parallel resonance. Okay. So if you've got any doubts, you can hang on for some time and then you can exit.
Thank you, sir.
Yeah.